Hi guys, I'm going to kind of make a video on how to do derivatives on the integers. So on, let's say, arithmetic rings. Okay, and I'm going to try and show how the kind of the idea between So I want to show you the ideas between this and usual derivatives. Okay, so let me give you. I don't know if I should just give you a big spoiler and tell you the definition. Okay, let me do it. Let me just give you the spoiler. Well, actually, let me give you. I don't know. Let's start with a derivation. Okay, so we'll take it. D is a derivation. So a derivation is well, you guys know what a derivation is. So let's say let's take A to be a ring and B to be an A algebra. So that means it's equipped with a multiplication by A on B, okay? And so a derivation from one of these guys to another guy's is a map of sets. And it satisfies, so for all, let's say, F, G, and A, right, it satisfies the following rules. So it has the sum rule, and it has this product rule. Let's say df times g plus f dg. Okay, everyone, so this is the Leibniz rule, the product rule. Okay, so this is a derivation. So let me give you a fact or a lemma or fact. Okay, so what we can do with the derivation is so there's kind of an equivalent way of looking at derivatives, okay, which I'm going to replicate when I do arithmetic derivatives, okay, and so derivatives and the ring of dual numbers and power series are friends, okay, so let me just say it. So let's say derivations from A to B. So again, this is the same setup as here. Are in correspondence with sections of certain ring homomorphisms. Okay, so let's see how. Okay, so let me say this. So there's going to be a map from A to the dual numbers of A. Okay, I'm writing this. So this is equal to A t mod t squared. Okay. Dual numbers of B, okay, such that there's this natural projection here. So that's a section. So let's say they're ring homomorphisms from A to here, such that this diagram commutes, and this is the algebra map. Okay, so this is the thing that is naturally given here. Okay, so it's almost like a section here. Okay, so so this is this is what a derivation is. Let me show you how this works. So let me write this down. So suppose. So I guess this is a proof. Okay, so suppose f is a map from here to here. Okay, so then what we can do is we can write f of a1, a2. Well, on one hand, it's f of a1, f of a2. Okay, and each f, right, we can break it down into two pieces. We can break it down into the piece where you in front of the epsilon and the piece that's not in front of the epsilon, okay, or the t in this case. And so this is, remember, working mod t squared, Okay, and this is as a module, this is isomorphic to as a module B direct sum B. Okay, so it's just like the stupid module structure here. Okay, and so now I can rewrite this. So this is f0 of a1 plus f1 of a1t. Okay, and then we have f0 of a2 plus f1 of a2t. Okay, and so this is mod t squared, so I can multiply this out, f0 of a1, f0 of a2, here, plus f0 of a1, f1 of a2, plus f1 of a2, or f1 of a1, f0 of a2, like so. T. Okay, and then we multiply these two together. The two t's cancel since we're going mod t squared. Okay, so now we have this big string of equations. Okay, and now let me write them out. So here. So then what do we get? So we get that f0 of a1 a2 plus f1 of a1 a2 t is equal to f0 of a1, f0 of a2 plus this crap again, f0 of a1, f1 of a2, plus f1 of a1, f0 of a2, t. Okay, these cancel, and this tells us that f0 of a1, a2 is equal, or f1 of a1, a2 is equal to f0 of a1, f1 of a2, plus f1 of a1, f0 of a2. Okay, so sometimes when we have just multiplication, so if f0 is the ring homomorphism from A to B, right? So this is the given ring homomorphism. We just write this as A1 F1 A2 plus A1 A2 F0 of A, or sorry, times A2. Okay. So this is just A2 here. And so if we replaced F1 with the D, so F1 is actually a derivation. Okay, and this is the idea. Okay, so you use these kind of like algebraic rules here for the ring of dual numbers to get derivations. Okay. So this is kind of a nice thing. So how do we get arithmetic derivatives? Arithmetic derivatives. Okay, and so this is Buium and Joyal. So this idea is due to Buium and Joyal. And actually this construction is quite ubiquitous in math. It appears in words like Morava E theory, right? There's like, so it appears a lot in K theory. It appears, these kind of constructions appear in the proof of growth and Riemann-Roch, and they come up a lot. Man, that's really bad. Okay, so the idea is replace this dual number functor. So this is a functor from the category of rings to the category of rings. So it takes a ring and it gives you back a ring with other functors, So other ways to cook up rings. In particular, we want, we are interested in the ring of Witt vectors. Okay, I'm going to make a video on rings of Witt vectors. So let me just say what the Witt vectors are for the truncated case, and then that'll suffice here. So recall. Okay, so if we have a ring. Okay, so we have a ring B, right? We make a new ring like this, where as sets here, this looks like B cross B. So it's just a set of B cross B. But it has some crazy, we give it, so we give some crazy, wacky, wacky addition and multiplication. Okay, so actually, so the rules. Okay, so it's like what we'll do is we'll take I don't know, we'll take A0, A1, and we'll add it using, this is like crazy multiplication here. Let's say B0, B1, and in crazy land, we're going to have some crazy rules here. Okay, and then here we're similarly going to have some crazy land multiplication. Okay, and so okay, so let me just say this. So here, it's not so crazy when we look at the first coordinate. Okay, the second coordinate will be a little bit crazier. So here, not so crazy yet. A1, B1. Okay, and then it gets crazy because I'm going to do this. So I'm going to do P over J, 1 over J, A0 to the P minus J, B0 to the J, from J is equal to 0 to P minus 1. And then you have A0 to the P, B. So this is the crazy rule in the second component. This one is here, B0 to the P, A1 plus P, A1, B1. All right. So these are the two things. So then the identity is going to be just like 1, 0. Okay, so sorry about that. I got interrupted for a second. So I was talking about these, and what was I saying? Oh, okay. I was talking about, so this is a definition. So we had this B. So what do I say? Okay, so this is the ring of Witt vectors of length 2. So this is a definition. Okay, definition / proposition. Okay, so the proposition part is that so the proposition part is that this is a ring. Okay, this is a commutative ring with identity. The proposition part is, the definition part is that for a ring, this is called the ring of Witt vectors. Vectors of length 2. Okay, so so this is a really cool construction. So it gives you these rings here, and the idea is to do so like it's the arithmetic analog of the ring of dual numbers. So this is this thing. Is the arithmetic analog. Of the ring of dual numbers. Okay, and so the ring of dual numbers again is this one here. So this is this B of t mod t squared, and this is the thing where you get derivatives. Okay, so now I can go and define what a p-derivation is. Okay, so an arithmetic derivative or Buium derivation, or so this definition is due to Buium and Joyal independently. It appears before this. So actually, maybe Joyal did it first, but this appears in Deligne and Luzzi's paper as well. So it comes up a lot. So a p derivation. So let B be in A algebra, and so a map from A to B is a p derivation. So this is a map of sets. So first of all, it's a map of sets. Then we say if it satisfies the following things, the axioms, right? So A1 plus A2 is equal to delta P of A1 plus delta P of A2 plus, and then I'm going to write this formula here, A1 plus A2 to the P minus A1 to the P, let's see, minus A2 to the P, so minus divided by P. So this thing here actually has integer coefficients, so you can expand this out, and then the binomial coefficients will be divisible by P. P is a prime, of course. And then delta P of A1, A2 is equal to A1 to the P, or sorry, let's do it like this. Delta P of A1, A2 to the P plus A1 to the P delta P of A2 plus P times delta P of A1 delta P of A2. Okay, and the third axiom is that delta P of 1 is equal to 0. Okay, so this has some interesting properties. Okay, so let me give you a fact. Okay, so the p-derivations from a ring A to B, so just like in the derivations case, so let me go back to the derivations case that we had here. So we had these derivations were equivalent to maps here from A to the dual numbers that satisfy this thing here, that satisfy this diagram, okay? So here we're going to do the exact same thing. And so there's a natural projection here, pi b, so from B, and then this is the algebra map. Okay, so again, we have B is an A algebra. Okay, and so this is the exact same type of correspondence that we had before. Let me say again why this works. So here we actually cooked up these rules to be exactly what we had, right? So this is really the sum rule, and this is the product rule here. So, and then this is this formula here. So i.e., given delta p p-derivation from A to B, we get a construct. What do we get to construct? We can construct a ring homomorphism so that takes A and it maps it to A delta P of A, right? And this is in the truncated Witt vectors of B, and then this is implied that this uses the algebra map. But here, so this is yeah, so this is a ring homomorphism from so this gives a ring homomorphism from A to WP of A, WP1 of B. Okay, so this is kind of the correspondence. So this is the idea here. So let me just give some examples. So examples. Okay, so on the integers, there's a unique one. And so what you do on the integers is you really take some integer and you do x minus x to the p divided by p. Okay, and so this is a new integer, and so this is like, okay, so note that by so for Moss' little theorem, that x is congruent to x to the p mod p, right? So so this means that x minus x to the p is equal to p times some crap, some junk, right? So it's p times stuff, right? So so this stuff is actually delta p of x. Okay, so that's the p derivation here. That's the idea. So another thing to think about, this is kind of like a derivative, because so mod p, this is 0 mod p, and this is 0 mod p. So p-adically, this is like 0 over 0. Okay, so let's look at this ring ZP unramified. So this is the maximal unramified extension of the p-adic integers. So that sucks, right? Because it's not really explicit. So, but this is just looks like where you join all these roots of unity, where p doesn't divide the root of unity. Maybe I'll do a video on like the algebraic number theory of these things. It doesn't matter. So here, I want to make a remark that this ring here has a certain lift of the Frobenius. So a lift of the Frobenius again is so this is just a ring. This is a ring homomorphism such that so that for all a in ZP of R, it satisfies that phi of a is congruent to a to the p mod p. Okay, so there's a ring homomorphism here, and its definition is that you take okay, phi restricted to the, so it's determined by the following formulas. So this is just going to be the identity, and so restricted to the, so this is, so ZP is the p-adic integers. So this is the inverse limit of z mod p to the n. Okay. ZP is this. Okay, and then on the roots of unity, you just take pth powers. Okay, so this is what we do. So this is defines the lift of the Frobenius phi. Okay, so then on this, so okay, this is the big aside here. So delta p is given by the following formula. Phi of x minus x to the p divided by p. And so you can check that this works. Okay, so there's lots of other examples. So let me say something else. So let me make a remark. So the constants, so okay, so when you have a derivative, so for derivatives, the constants of the derivation, so let's say we have a derivation from a ring A to itself, okay? Then it turns out that if we call AD, so this is the set of A and A where dA is equal to 0, so this is a derivation, then this is actually a subring of A. Here, for p-derivations, there's something weirder. So delta p from A to A. So the A of delta p. Okay. So this is actually, okay, this is the same thing, right? Okay. Here, this is actually a monoid. So maybe a submonoid of A. Let me give you an example. In the previous example, when A is this ZP unramified, okay, then the monoid is equal to, this is the roots of unity. So this is zeta, so such that zeta to the n is equal to 1 for p not dividing n. Okay, and I think union is 0, because delta p of 0 is 0. Okay, so this is the monoid of roots of unity. Let me show you how this works. So, well, let me just show you that this is this containment. Okay, so so just look at delta p of some guy here. Okay, some root of unity. Okay, so by definition, this is just this minus this to the p divided by p. So that was what we defined here. So that was this definition. Okay, and so, and yeah, and then we had this definition of the Frobenius here. So the lift of the Frobenius. Okay, so here's what we have here. so then this looks like zeta to the p minus zeta to the p over p, which is 0. Okay, so that's what the p derivation looks like, and this is actually true in general. All right. Yeah, so I think I might add some more to these things later. I want to talk about ring schemes and how. Let me show you that. So in both of these definitions here, we have this definition, we have this definition. Let's see. Okay, so we had this definition here, and so we had this map to this ring scheme. Okay, and then here we also had maps maps to the dual numbers. And this is also a maps to a certain formula here, like to the truncated Witt vectors. And it turns out in general you can formulate these things. And so there's some theorems by Buium about like what types of operations you can have where you have some like sums and product rules. And yeah, and I'm gonna want to talk about that. So thanks for watching. Hope you enjoyed it.